Hi, I'm Jim Heffron. These are my lessons in Calculus 1. So the next two sections we're going to cover quickly, so we're going to cover them as smaller sections, and as a result we're going to combine them into a single homework. I'm still keeping the sections separately just for neatness so that a person can find where it is, the material that they're looking for is, but going to be a little shorter than the average day. Okay, great, let's get to it. So we want to talk about linear approximation today. So we're always coming back to derivatives, and so we're thinking about the tangent line. And in particular here we see the picture with the tangent line. See the picture with the tangent line and the function, and we see that the tangent line is quite close to the function, so we will often in calculus use the tangent line as an approximation for the function. Here, this is one way to state that idea. We know how to find the square root of 4 or the arc cosine of 1, but how to find an arbitrary value such as the square root of 4.2 instead of the square root of 4, or the arc cosine of 0.9. Okay, so we have to think of some way to find those numbers. So the natural thing to do here is to let f of x be the function of interest. We're thinking about square root of 4, so I'm going to think about the function square root. And if you take the derivative of f, then of course you get 1 over 2 square roots of x. We've done that lots of times now, so it's familiar. At the point 4, 2, drawn on the picture, at the point 4, 2, the tangent line is y minus 2 equals 1/4 times x minus 4. You can write it in mx plus b if you like. Move the 2 over. Okay, and that's all routine stuff. We've thought about that lots and lots of times. But I want you to look at this picture. So in this picture, if I, for example, focus on inputs between 3 and 5, the tangent line is very, very close to the function. So close that, in fact, you can't really tell them apart here. If you look at input x's, you can't, maybe just at the very edge down here at x equals 3, or just at the upper edge here at x equals 5, you can just kind of tell them apart. So the tangent line is a very, very good approximation for the function, and it has the advantage that it's easy to compute. So if you don't know how to take the square root of 4.2, you sure as heck can plug 4.2 into the tangent line equation. So that's exactly what I did. I plugged 4.2 into the tangent line equation, and I got out a perfectly good value, 2.05. It turns out that 2.05 is an awfully good approximation of 2.049390, etc., of the square root of 4.02. So we can use the tangent line as an approximation for the function, and one way to make that point sort of concrete is in this section we will show how to approximate values by using the tangent line. But again, we're trying to think about an underlying idea, which is that the tangent line can be used as a surrogate for the function if you're close enough to the point of tangency. So definition, the tangent line approximation, sometimes called linear approximation or linearization or first order approximation. That's a phrase that you'll see more in calculus 2. To a function f at an input x equals a is just the tangent line. So this is the equation of the tangent line. I've given it the name capital L, but this is the equation of the tangent line. There's the slope, there's x minus x1, and here's y1. Okay, so now we're going to see a bunch of examples. So I'm going to give you a bunch of examples, and in order to do these and any of the homeworks, what you do is you consider the natural function. On the prior slide I considered square root of x, and you find a nearby point a where you can evaluate both f of a and f prime of a. On the previous slide, that nearby point was a equals 2. Okay, let's give it a whack. So I want to use the linear approximation to estimate natural log of 1.04. So it's easy to compute the natural log of 1. What e to the 1 equals 1, you say, well, e to the 0 equals 1. Great. But what about 1.04? If you were making up a table of logarithms, how would you compute the natural log of 1.04? It turns out when you plug it into your calculator and you get out an answer, it's about 0.0392 to 4 decimal places. Okay, so we've seen the deal here, and the formula is at the top of the slide. I meant to circle the formula. There we go. Circle, 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 circle. There we go. So you find the tangent line at the nearby input a equals 1. So that is to say, you consider the function f of x equals ln x at x equals 1. And then you think about the tangent line equation. So that's what we did. Here's the tangent line equation, and I plugged in the parts. Natural log of 1 is 0. The slope there is 1, x minus 1. And when all the smoke clears, there isn't much smoke to clear, but when all the smoke clears, this tangent line here has the equation y equals x minus 1. Okay, quite clearly has a slope of 1 and has an intercept, if I was to continue it, there we go, intercept of minus 1. So all I got to do now to find my approximation for the natural logarithm of 1.04 is to plug 1.04 into this formula. And when you do, you get 0.04, and that's awfully close for very little effort to 0.0392. Okay, so again, of course, we want to know the value of these numbers, but there's also a larger point, which is that we are using the tangent line as a surrogate, taking the place of the function itself. Another example, 1 over 4.005, and I wrote out its correct value to a ridiculous number of decimal places. Look at that. Okay, so here the function that you would think about, I think, is the 1 over function. So f of x equals 1 over x, and you would think about at the point a equals 4. Okay, and then plug into the formula. So that's exactly what I have in mind. So I took f of x to be 1 over x and a equals 4, and I plugged into the formula. There's the formula right there, copied over from the prior slide. So I got f of 4, and then f prime of 4, and x minus 4. And when you plug in 4.05 into that formula, you get an approximation that is, again, I copied that out to what, 7 decimal places? Oh, so I'm looking up here to the actual correct value. So let's see, 0.249, that's good. 687, that's good. And here it says 5, whereas up here it says 8. So awfully good approximation. So again, we're seeing that you can take the tangent line to be an approximation for the function within bounds. Now, a person who is quantitatively minded, everybody in this class, in other words, will say to me something like, well, how good is the approximation? And over what range can you clearly can't plug in a equals 100 and expect good answers there. True. Now, the exact numbers there that a person would study in a class such as numerical analysis, those are beyond our scope. But we're trying to give a kind of a general setting here, and the general setting is you can use the tangent line as an approximator of the function. Exactly how many decimal places, that's beyond what we're thinking about at the moment. Okay, as you know, I like to give folks a chance to practice this, so before they get to the homework, they have some sense of what's happening. So I have two practices on this slide, and I urge you to pause the video, give it a try, and come back. Okay, cube root of 8.1, so the natural thing is to look at f of x equals cube root of x, and a equals 8. Then you plug in the equation of the tangent line. There it is, equation of the tangent line, the first order approximation equation of the tangent line, and when you do, you get 2.008, whereas for comparison on a calculator, cube root of 8.1 is 2.008 and then a 299. So awfully good. Okay, one more question here, the sine of theta, where theta is 44 degrees, and you'll notice, we've talked about before in here, you'll notice that you want to do calculus in radians, so you want to convert the degrees to radians. Okay, give you a second to give it a try. Okay, great. So here is here's the equation of the here it is, the equation of the tangent line. There we go. And I thought that the nearby point of interest is going to be the 45-degree point, so the pi over 4. All right, so I'm looking at the sine function for f and the pi over 4 for the point of interest. And then the derivative, of course, is cosine, and so f prime of pi over 4 is square root of 2 over 2. If you convert 44 degrees into radians, you get 0.768, and so we end up with a number of 0.695. Okay? So, of course, there's a little twist in this problem that you have to convert the degrees to radians, but it's not much of a twist, especially since the hint says convert to radians. Okay, I want to talk for a minute about something that the book talks about and will sometimes occur in other classes and in classes that follow this, but I'm going to de-emphasize it. You can't emphasize everything, but I do want to at least mention it in passing. So differentials. So let's see. I want to talk about the history here just a little bit. There's a picture of Johann Bernoulli, who not only was famous researcher at the beginnings of calculus, but also was a teacher of Leonhard Euler, so he was famous for several reasons. When limits were not yet developed, people thought like this. Well, for small x's, we have that dy dx, delta y over delta x is about the rate of change, and when the numbers, the delta x's become so very small that they are, quote, infinitesimal, unquote, the approximation becomes an equality. People are thinking this, their first steps in the subject, they haven't got everything exactly precisely right. They're pretty good, but haven't got everything exactly precisely right. And so they thought like that delta y over delta x becomes, when delta x becomes very small to be infinitesimal, becomes a dy dx, which is equal to the rate of change, no longer an approximation of the rate of change. And people spoke of dy and dx as being differentials. So I want to give you some picture of what a person could mean by that. It's a first understanding of what a person could mean like that. So here's the usual a f of a and a plus delta x, f of a plus delta x picture. Of course, there's the delta x and the delta y. Very familiar picture. Okay, and now here's the differential picture that a person might write. They've zoomed in on this spot, I guess, zoomed in on this spot so very close that it no longer looks like a curve, but instead looks like a straight line. And so at that point, a small increment in the input and a small increment in the output are related this way, that if you start at A, and you go some tiny increment in the input. So if you start at A, oops, I regret writing now. If you start at A and you go some tiny increment in the input, then what happens is you bump up by dy. So if you start at an input of A, then of course you're at f of A. If you go some tiny increment in the input, you go up by a dy. So one way to think of dy is being a variable that depends on x and also depends on dx. Okay, so again, the difference between these two pictures is that this is a straight line. Okay, when this is obviously a curve. And if you think that's a little on the vague side, yes it is. That's as precise as I'm going to get with differentials. Okay? Okay, very good. So the summary here is that the delta y over delta x ratio is from a secant line, while the dy over dx ratio is from the tangent line. And if you hear people referring to dx and dy as separate variables, as you might, for example, in a physics class, a rule of thumb for us is that you can take dx to be a very small increment in the output. So the way I think of it is 10 to the minus 5. And of course, that's impossibly vague, but I'll just say 10 to the minus 5. And you can take dy to be the associated small increment in the function's output. And then at the bottom, I made a comment because I feel tremendously guilty not giving it the full treatment. But you can't give everything the full treatment. It's perfectly possible to make mathematically precise sense of expressions like x plus 2 dx. But that's simply outside of the scope of this course. We're just simply not going there, and that's all there is to it. Okay, very good. So again, when we come in, so no homework for this. When we come in the next time, I'm going to do another section, which we're going to do quickly. It just doesn't contain much material, and then I'm going to combine the two sections together into one single homework. Okay, very good.